Hello everyone. Hope you all are staying safe and healthy. This is Manasi Pisar from Department of MCA on behalf of VSIT. Welcome all of you on today's session of the event We Reach 2021 Alumni Engagement Initiative. Now, I would like Professor Dhanamma Jaglu to give us an insight on today's session. Over to you, ma'am.
Good evening everyone. I welcome you all in VReach 2021 session. VReach is Alumni Engagement Initiative by VISIT under the guidance of VISIT IQAC. Today we have Mr. Jason Varghese with us. He is a Senior Software Engineer at TIAA. He has completed his MCA from VISIT in the year 2013. Today he will be speaking on cloud computing using microservices architecture. Over to you, Jason. Thank you.
Hi, this is Jason Verghese, and today we'll be talking on the topic cloud computing using microservices architecture. So, without further ado, let us look into the agenda for today. So, first of all, we'll be talking about why we need microservices in the first place, right? We need to understand why we need to adopt this new microservices architecture. Then we'll be talking about what is microservices architecture and what are its various features. We'll also be talking about its advantages. Then we'll move on to another industry technology, that is CI/CD, or continuous integration and continuous delivery pipeline. After that, we'll talk about cloud and the various components used in the industry. And then we will see how we can use all of these technologies together in a combined way and how all of them works together in a seamless way. So let's start. Okay, so let's understand why we need microservices in the first place. Microservices architecture are being used by small and great software companies alike. Earlier, companies used to use monolith architecture, but now architecture is much more efficient. And so, great companies like Amazon, Netflix, Twitter, Uber, as you can see, all of them are using microservices. At the same time, there are companies like Netflix, Twitter, who have even published their own microservices tools and frameworks for the world to use. Also, most of the software industry is pushing towards private, public, and hybrid cloud deployments in the cloud environment using automatic CI/CD pipelines, right? So, computer science freshers equipped with the knowledge would certainly have an advantage in the job market. We can see over here the average salary of senior software engineers and software engineers equipped with the microservices skill, and so it's really an advantage for job applicants to know about this technology. Now, what is microservice architecture? To understand that, you have to first understand the previous architecture style, that is the monolith architecture. What was the monolith architecture? Let us take an example of a monolith application. Here, Alice wants to watch a TV series on MediaMore.com. Now, MediaMore is a similar service like Netflix or Amazon Prime, which we have watched. We all understand that such a huge software system will have a lot of components, like, for example, the video streaming component. There would be another component for just showing the recommendations, which would be using AI or ML. And there would be another system or component which stores the user details, right? So there will be several such components in such a system. Now, in a monolithic architecture style, all of these components will reside in a single code base. The recommendation system code, the code for viewing the videos, as well as the code for purchasing a new subscription, all of those codes will reside in a single code base. Okay, so all of the business functions will be part of the same single code base under a single database. Okay, so that's what we can see over here in this. Now, when we adopt this monolithic architecture style, there are a lot of problems that comes up. Okay, so what are those problems? First of all, is large and complex applications. The code base becomes so huge because there is all the components stored in one code base. So there is the recommendation code, there is the video streaming code. All of them are huge code. So the code files might be hundreds or even thousands of code files in just one project, which means that any person, if he has to, any developer has to understand the code base, it will take a lot of time to understand the code base. Second, it's very tightly coupled, so that if you have to change some part of the code, it's not very easy. Okay, because it might impact some other place. So that is the first disadvantage. The second disadvantage or challenge is that it leads to slow development. That is because all the components are in the same code base. So the recommendation team as well as the video streaming team, all of them have to work on the same code base. And so it results in a very slow development because teams have to synchronize with each other. They have to commit together, they have to merge, and they have to make sure that all of the code works seamlessly and after test. Okay, and secondly, the IDE becomes slow because of the huge number of code files that are present. So I had in my project uh, really a hard time when I had similar monolithic architecture and the application used to take around 20 minutes. I'm not joking. It used to take 20 minutes for the application to start and show the UI. Okay, so any small change you used to do, you had to be exactly very sure of the change, because otherwise you have to again wait another 20 minutes to make the correction. So that's the code size that is there. At the same time, it was very brittle, right? It's highly cohesive and highly coupled code, so it's very brittle. It also blocks continuous development, meaning that you can't update an object in isolation. If you have a small update in a component, you still have to update the entire application. And sometimes that small change could have an adverse effect on some other component, leading to a risk. So that is why companies are hesitant to even adopt fast releases. The next challenge with monolithic architecture is unscalability. Now, what is scaling? Now, we know that websites serve traffic, but there are cases like Amazon Big Billion Day, right? You have an increase of traffic. Okay, in this web page, you can see a sample e-commerce website. It has a customer service, it has a cart service, and it has a product service. Right now, this entire thing is a one application, and all of the three components code is stored in one application. Now, if suddenly there are a lot of complaints, and so the web page, just the page for the customer service, gets a huge surge of traffic, right? Now, usually what happens is that the an increase in traffic is detected, and they can create new servers that has the same code. Okay, so if the traffic has increased two times, you can you can add two servers or three servers to handle the increased load. Okay, so this is possible in monolithic architecture, but the problem is that you can't scale up the individual services, right? You have to scale up the entire application, right? So if only the customer service module has to be scaled up, there is no provision. You have to scale up the entire application containing all the code of the three components, right? This is inefficient. The other thing is that you can't scale based on the requirements, like memory requirements, CPU requirements. Like for example, there might be some components that need a lot of CPU versus some components that just need a lot of memory. Okay, so maybe you can customize that. But that customization is not available in a monolithic architecture. There is only a single server that's common for all the components. Okay, the next challenge is that it is highly unreliable, meaning that now there are three components: customer service, product service, and cart service, all of the three components in one application. Now, supposingly the customer service got some error and it came down, that particular service is not working. But now it's not that just that service, it is the entire application along with card service and product service that is gone down. This is because the entire code is tightly coupled. All of the components are tightly coupled with each other, and if one of the components goes down, the entire application goes down. So monolithic architecture is highly unreliable. The next challenge is that monolithic architecture are highly inflexible, meaning that it's very hard to adopt new frameworks or technologies into the software system. For example, some of the components might be more better to implement in a particular framework or technology, and maybe some component you want to implement in another technology. It is not very easy or efficient to do that. At the same time, if you want to implement a new framework, even though it is very good or beneficial, companies would hesitate to implement it because it would involve a lot of cost in terms of time, effort, and money and resources, because you have to change the code of the entire application. You can't make changes in isolation. You have to change the framework or the technology of the entire application. At the same time, there might be some components which are more efficient in a certain technology, right? So such isolated implementation is not possible in monolithic architecture. Okay, so finally, we can now understand what a microservice architecture is and how it solves all these challenges and problems. Microservice architecture is a style of developing software where you don't develop the software as a single component, but instead you break down the application into small web services called microservices which interact with each other. And each of those microservices is modeled around a business function or a business domain. For example, with respect to our video streaming service, recommendation is a business function. So you have one microservice dedicated to recommendation. Let's understand this more in detail in the next slide. In the previous example, we had learned about the MediaMole.com, which had several components, but all of them was combined as a single code base. But in microservice architecture, we will split up that entire application into individual microservices, and each of the microservices will be serving one particular business function. For example, we'll have one microservice for the video streaming part. There will be one microservice for the recommendations part. There will be another microservice for the ratings or similar business components. Okay, and each of these microservices are independent of the other, and they communicate via REST or messaging. Now, what is the use of such architecture? Is that, for example, if I take Amazon, right? There are people that are that are looking at the products. At the same time, there are people that are checking out the products on the cart. So, if the cart component and the product catalog and all of the components was a single monolithic application, right? Then if the cart component goes down, then the entire Amazon app goes down because it's a monolithic app. But if I were to break the app into each microservice, right, then supposingly if the cart component goes down, that only that particular microservice goes down. Okay, only the users that are on the cart and checking out the products will be impacted, but the users who are browsing the catalog will not be impacted, and the users who are writing a review system, they can still write the review because those microservices are still up. So basically, this particular architecture style makes each of the components independent of each other. So at the same time, in front of your slide, you can see the different components of a microservice architecture, which is really important. Okay, first of all, we can see an API gateway which is sitting in front of all the microservices, right? So as I said, each microservice is independent of each other. They are stateless. That is, uh, each transaction that you hit onto the service is independent and doesn't know of any other previous transaction. It is stateless, because usually it is a REST call and or messaging call, right? At the same time, you this API gateway sits like a front door or like a gate in front of the application. So what it does is basically it gives a single URL for the outside world to access the microservices. Okay, so it's a single endpoint. At the same time, it also does common functions like security, it does logging, and it does many other services. It also does load balancing, so wherein the traffic is distributed across servers equally, right? So you can also see there is a CDN here. CDN is basically content distribution network, wherein you have the content stored most closest to the user. Okay. Okay, this is another slide wherein you can see the comparison side by side of monolith versus microservices. On monolith, you can see the UI, user interface, the business logic, and data interface. All of them are clubbed as a single code base, which is interacting to a single database. But in microservice architecture, you can see that the user interface is a separate microservice. Uh, there are other microservices, and the data is federated. what do, what do you mean by federated is that there each of the microservice has its own data model. Okay, so unlike the monolith, it doesn't have a single database, but each microservices has its own data model and its own database or some other data repository. Okay, so this is the overall architecture style of microservice. Now let's understand the features of microservice architecture. First of all, microservice is small focused. That is, it is focused on simplicity. Any developer can focus only on a particular business domain and do any enhancements or creative work on that particular business domain only. He doesn't have to think about the other components of the system. Second, it is loosely coupled, meaning that each of the microservice is independent of the other, right? If one component goes down, if the cart component goes down, the product catalog is still up. So they are independent of each other. Thirdly, it is language neutral. So in case if you want to have one microservice implemented in Java because it has extensive library, and want another microservice independent on Python, then it is fine. Okay, all of them will communicate each other with REST or messaging. And the last one is bounded context. Bounded context means that each of the microservice doesn't need to know how the other microservice is implemented. And at the same time, it is bounded for a particular business. Now let's understand the advantages of microservices architecture. First of all, we have independent development. So for example, in our Amazon example, the dev team of the product catalog doesn't can work independently of the dev team of the cart component. And similarly, for there is independent deployment, right? Across the environments, the dev teams can deploy and they independent of the other teams, right? And then there is fault isolation. Now it's very easy to isolate a particular error, because now we can quickly find out which particular microservice was failing, right? The next is mixed technology stack, which I've already explained. And lastly, we have granular scaling. Granular scaling is basically that you can scale individual microservices. So for example, if there is a high number of traffic on the product catalog, a lot of people are searching the products, then you can just scale the product catalog microservice, and the cart service and the other microservices can still be, having just one or two servers, while the product catalog can be scaled to multiple servers, 3 or 5 servers. So as you can see that microservices are really useful for small and large businesses alike, and this is something that all of you will see in the workforce, that it is highly being used these days. In front of you is the service mesh of Amazon and Netflix. That is, each of those boxes or squares in this globe is actually a microservice. So this is published by the individual companies itself. So as you can see, there are thousands of microservices, if not more, that they have published, and each of them interact with with each other and serve a particular function. So this is a trend that is here to stay. So I hope you all got a good idea of what microservices is. Another new concept that students entering into the workforce for the first time will really find new is about CI/CD, that is continuous integration and continuous delivery. Okay, so what exactly is this concept? We all know this SDLC cycle, right? We have requirements, design, implementation, testing, and evolution. So in this, after implementation, the coding part, after that is done, CI/CD helps to take that code and put it onto the servers, right? So there are a lot of phases that happen once your code is ready and it is deployed onto the server. So CI/CD helps automatically do all of this. But before we understand how it is done through CI/CD, we have to understand how it was done traditionally to understand the beauty of CI/CD. Suppose we have a website called Mike's Electronics website. Okay, and there's a team of software developers who have finished their code and they are ready to deploy it onto the servers, right? But they can't directly deploy it. They have to complete a lot of tests, and the code has to pass all the unit tests and integration tests. Okay, so how does it happen in the traditional way? First of all, this code, since it is created by multiple team members, we need a code versioning system, for example, Git, so that everybody can synchronize their code and there is a single repository, right? So they check in their code into Git. After that, the code is compiled into the respective compiled version. Like for example, if it's Java, it's the class files, right? And then the compiled code has to be then packaged. So what do you mean by packaged is that in case of Java, uh, you make a war out of it, right? Or you make a jar out of it. So that is the final deliverable. So it will be different for other .NET or other languages. So after packaging, once the package is ready, we inform the operations team and they take this package and they firstly deploy it onto a test environment. And once it is deployed on test environment, the testers come and test the functionality. They check if all of the functionality is working as per the business requirements, as well as there are no bugs in the code. So once that is done, if the testers give a green light, we go ahead and publish the website onto the production. Again, the operations team does that. There would be a different set of configuration for the production environment. But if there is a bug, it goes back to the development team, and again the cycle repeats until all the bugs are resolved, and then the testers give a go ahead for the production deployment. In the previous slide, you would have noticed a lot of inefficiencies and manual steps. The compilation, packaging steps were manual. Also, the operations team had to manually take the package and then deploy it along as per the appropriate configuration onto the test server and then later on to the production server. I remember from my first project that this particular step is particularly error prone as well, because we used to sit with the operations team and make sure that they take this artifact and they put in the right configuration. And sometimes there would be some kind of typos or something that would just break the deployment, because the operation team would have to actually log into the servers, Unix servers, and then they had to deploy the war, and then they had to start the servers. It was very error prone. But now, using CI/CD, tools like Jenkins and other tools have made all of these steps automatic. For example, as soon as if you see in on the slide, customer profile, product catalog, and these three teams, right? As soon as they check in their code, it will get onto the Git repository or whatever version control system you use, and that triggers an automatic compilation step and packaging step. This is done on a server called the build server. Okay, so this is Jenkins is one of the companies which provide this build server, which automatically sees that a check-in has happened, which the check-in triggers the compilation and the packaging steps. Okay, so that part is automated. In the next step, after the package is created, the code now is automatically tested. All the unit tests that were developed by the developers are run, and if there is any test that has failed, the appropriate team or developer can be notified using an email. Okay, and the build stops there. It doesn't go ahead in the stages. Okay, so that leads to additional code quality, better code quality, and at the same time, all of this is very automatic. As soon as the developer checks in the code, it goes to Git and then gets compiled, packaged, unit tested, and if it passes, then it goes ahead into the next part. Okay, but as of now, all of these steps are taken care of by the build server automatically. Now, this series of steps which we just saw is called continuous integration, wherein all of these steps are automatically executed by the build server. The code, right from the time it is checked in until the time it is unit tested and packaged, is called continuous integration. After continuous integration, we have to take this and get the artifact deployed onto various servers. Now, this was also a manual step where operations team had to manually deploy, log into the servers and deploy the artifacts. But now, using the CI/CD pipelines, this also is automated using automated scripts. As you can see, operations team develop automated scripts which take in the war or whatever artifact that is generated by the previous step. They take that artifact and automatically the script deploys it onto the test environment based on the configuration that is provided by the developers. Once it is in test environment, the QA is notified and they can test it. And this part of the step is the only manual part where the testers have to go in and test it, right? That is the testing part that we can see. And if the testing passes, it goes to the public website. Now, in this entire sequence, we see that there is only one step that is manual. But that so far is called the continuous delivery, wherein all of the deployment is made automatic except for the testing part. We can make this whole process even more efficient by automating the last manual step, that is the testing part. So in this, the testers create test scripts or test code that automatically test the code once the code reaches the test environment. Okay, and if the test pass, the code is automatically sent ahead to the public website or the production servers. Okay, now this has to be handled with care, because here here we are automatically deploying it onto the production servers, but this requires a high level of maturity for all of the teams that are working. At the same time, we can also have a stop at the automated test step if we want. But if we are making this whole process automatic, then that means we have reached the continuous delivery step. That is, the entire series of steps from the check-in of the code till the deployment onto the public website is fully automated and without any manual step, leading to more code quality with automated testing, as well as less less wastage of time waiting for different teams. So this entire pipeline in one page you can see is the continuous deployment, wherein as soon as the developers check in the code, all of the series of checks and balances are executed and the final code is deployed on the website. This is continuous deployment. So there are these three terms that we have to understand in this CIC. So the three terms are continuous integration, continuous delivery, and continuous deployment. Right? In this, continuous delivery and continuous deployment are almost the same, except that in continuous delivery, the testing part is manual, while in continuous deployment, the testing is automatic. These are some of the tools and technologies used in the industry for performing CI/CD, and all of this can be managed by Jenkins. Right from the time the code is pushed into GitHub and then unit tested and then integration tested and deployed onto different servers. Here we can see a simple company project, a very real life example of how CI/CD is set up usually. So once the code is checked in by the developers, it reaches some kind of version control system like Git, which triggers a build on the Jenkins pipeline. And Jenkins performs unit test, integration test, it packages the war and does all of those series of steps which we discussed, and then it gets deployed onto the server. Now, since we are talking about microservices and cloud, let's assume that it is getting deployed on a Docker container, right? So uh, to deploy it on a Docker container, we have to create a Docker image. Now, this Docker image will contain not only the project's code, it will also contain the project's configuration, any other libraries that the project has used, and all of this along with the operating system, which is very small in terms of Docker containers, and it is very lightweight compared to VMs. And all of that is created as an image, and then it is deployed onto a container. And this same container is then moved, or I should say this same image is then moved across different environments, from dev to the testing environment, to the performance testing servers, to the production servers. The same container is moved across the servers. So this helps, to keep a uniform code. There is no way that we can have some kind of environment issues, because all of the environment dependencies are contained inside the Docker image. It contains right from the operating system till the project code, everything is contained in that. Okay, so let's talk a little bit more about the cloud components of a typical Docker Kubernetes stack. So we have reached the final subsection of this talk. As I've already mentioned, that all the companies are moving towards cloud deployments, whether it be private, public, or hybrid cloud deployments. All of the companies are moving towards cloud because of the lot of advantages that it provides. So, as computer science freshers, it is very important that we understand the cloud stack and all of the different technologies that it uses. So, after that, we will quickly wrap this up, and then we'll just talk about how microservices, CI/CD pipelines, and cloud, all of them work together in a very seamless way. And this is currently the industry trend, wherein all of the companies are moving towards microservices, CI/CD, and cloud deployments. So let us look into it. So here we can see a cloud stack example, a typical way of implementing cloud in the corporate environment. So we have everything, the Docker container, Docker pod, Kubernetes, and Red Hat OpenShift. There might be slight variations from company to company, but this is a complete cloud stack. So at the very bottom, you can see the Docker container. You all would be familiar with Docker container. If you're not familiar, I would recommend you to watch another talk on the same channel by Prabhanak Nair last year, which explains it in detail. But basically, a Docker container is a running instance of a Docker image. So basically, it contains your project as well as the OS dependencies and any other libraries and frameworks that are required for the project. But it's very lightweight. Okay, so that's the Docker container. Now moving up, we have the Docker pod. Now one Docker pod will contain multiple Docker containers. And Docker pod is more of a way to organize the Docker containers. Okay, so also one interesting fact is that a pod is a group of whales. Okay, so the Docker logo is a whale. So a Docker pod is a group of Docker containers. Okay, now above that we have Kubernetes cluster. Okay, now one Kubernetes cluster. Okay, what is Kubernetes? Kubernetes is basically a container orchestration service. So what it does basically is it controls a lot of Docker pods. Okay, so it manages the Docker pods, it creates the pods, it deletes the pods. It brings up the server, it decommissions the server, all those things, right? So, for example, if one of the Docker pod goes down, right? Kubernetes cluster will automatically understand that it has gone down. Kubernetes will know that, and it will automatically bring up another pod with the same code, with the same containers and all of the same stack, right? So Kubernetes understands that, and that is why it is called a container orchestration service. It does a lot of other things, but the Kubernetes is one Kubernetes cluster contains multiple Docker pods. Now, above Kubernetes, we have Red Hat OpenShift. Now, Red Hat OpenShift is basically an enterprise support or an enterprise version of Kubernetes. That is, it gives a kind of enterprise support to the Kubernetes, because Kubernetes is basically free, and so Red Hat OpenShift, there is no kind of support for Kubernetes. So Red Hat OpenShift gives enterprise support so that companies can reach out to a team for any kind of issues. Okay, so that is a complete stack. Red Hat OpenShift contains multiple Kubernetes cluster. Now, let me combine everything, right? The first topic that we had talked about was microservices. Now, how does microservices fit in into the stack? This one microservice, for example, in our example of MediaMore, where it had a recommendation service, right? Or a video streaming service. So one such microservice will have all of this stack. Okay, so one microservice will be deployed on one Red Hat OpenShift server, which will have multiple Kubernetes clusters and which will have multiple pods and multiple Docker containers. So that is how all of it fits together. Okay, so let me explain it in further. So let us bring all the technologies that we discussed today, right, and how it works together. So let us see how microservices and cloud and CI/CD are all implemented together, right? So in our first example, we had seen MediaMore company had implemented microservices. Now we can see that the video streaming service is a separate microservice, and the recommendation component is also a separate microservice. Now, how is this implemented in cloud? Now, each of these microservices is deployed on its own OpenShift cluster. So, for example, the video streaming microservice will have its own OpenShift cluster, which will have its own Kubernetes cluster and pods, and which will in turn have multiple Docker containers. So that is the way it is implemented. And the thing is that it is very highly fault tolerant. That is, if one of the pods of the video streaming service goes down, automatically Kubernetes brings up another pod in its place with the same code and libraries. So it's highly tolerant, and there are a lot of advantages. This is just the start. And how does CI/CD come into this picture? CI/CD is basically a pipe that pushes in content into all of these servers. So as soon as the developer checks in the code, it does all of the tests and balances, and then it deploys the code into these Docker containers, and which then the server starts up and the code is live. So that is the way microservices, cloud, and CI/CD all work together. And this is the way the industry is also moving towards cloud, towards microservices and CI/CD. And I'm sure most of you would see these kind of architecture and its variations when once you join the workforce. So that's all from my side. I hope I was able to give you a broad overview of how all of these technologies work. If you have any questions, please do reach out to me on the email which I've given. Currently, in my current profession, I'm using all of these technologies, and I have really life has become much more easier because of all of these automatic builds and automatic pipelines, CI/CD pipelines, and cloud deployments. There's a lot of improvement, and this is the way the industry is going to move in the future as well. So thank you, everyone. Thank you for your time. Thanks.
Thank you so much, Jason. It was indeed a very interesting session and a very innovative explanation that you gave. So, as we are done with the explanation, let's move towards the questions that our viewers have for you. Yeah. So, we have our first question. So, the question is, sir, does the benefit of easy scalability and maintainability overcome the cost of maintaining different code bases and integrating those along with having skilled developers of different code base?
Yes, to your answer to your question, yes, it really has an additional advantage. So there are two parts of the question. So I'll answer the first part, that is scalability and high availability. So definitely both of them are really important for every company. Every company wants their website to be 100% up, no downtime should be there. So they definitely want highly availability and scalability, because if there is a surge of traffic, they really want there should not be any slowness in the websites or in their APIs. So that is the first part. The second is with respect to code bases, and I think code bases, having multiple code bases is an advantage, because now companies have multiple employees and multiple teams, so they can have one team work on one component, one business component, and that particular team can actually have its own code base independent of the other teams, so they can check in and they can deploy their code bases, and they won't have merging conflicts, or they don't have to check if their code is impacting some other code of some other team. So that really is an advantage in microservices to have separate code bases. But if you see in monolithic, they all of the teams are checking in code into the same code base, which results in a lot of maintainability issues and each team has to merge their changes before they check in. And there's uh, in the long run, maintainability becomes an issue. But in microservices, both of that, uh, uh, we have separate code bases for each team, so that really helps in having independent, workflows.
Okay, so I hope that was helpful. So the second question is, sir, is it that Jenkins and Kubernetes can be used only for loosely coupled applications?
No, that is not right. Jenkins is a build tool which basically does, you can automate a lot of things with it. It could be compiling code, packaging code, yeah, testing the code, having unit tests, integration tests, or different kind of validations. Docker image is correct or not? Is it as per the company standard? So those things, yeah, those things can be validated. So Jenkins will work even with a monolithic application. Okay, and even for Kubernetes, it's the same. It will work with monolithic or microservices architecture. But the thing is that the industry is moving towards this new frameworks, and it really helps that Kubernetes will have its own, microservices, and have be small focused, as I said, to be simple, and just do one business component each time and not do everything, so that we get all the advantages.
Okay. So the next question is, which are the most used languages or frameworks for making loosely coupled applications or implementing microservices?
So most used, when you say, actually, or any technology or any language can be used for these microservices. These are language or framework agnostic. So any kind of technology, be it Python, Java, .NET, everything is now moving into the microservices world. So whatever are the most popular technologies being used currently in the market, this will also be same for the microservices world. So that's not a change. It's very agnostic. That it's very language agnostic and language neutral. So I hope that answers your question.
Okay, so the next question is, so by loose coupling, unit testing gets easier, but don't you think so integration testing might get tough with implementing microservices?
Right. So there are a few things that could be a problem, like integration testing could be a problem, because you have to test all the components and all the microservices, and that is a different way. In monolithic, it was much easier to do integration testing. So that is one of the small things that has to be noted. But compared to the many benefits in terms of having, scalability, highly availability, and a modular code, and having separate teams work on each component, that really is an advantage. And in the long run, it it actually helps in having more tested code, because now teams can actually only test their code and focus on making that part right. And if that part is right, the other components, like each microservices talking to each other, right, is basically using REST or messaging, and that really doesn't have much issues, and that really doesn't cause much of the problems. But most of the advantages, there are several advantages that really overrides the small drawbacks that are there.
Okay, so that was probably the last question we had. Is there anything else you would like to add or to tell everyone who's watching?
Yeah, I was really impressed by the quality of questions that was given, and I really want to thank all of the viewers and the questionnaires for giving that question. I hope you all have learned something new from this session, and I also want to thank the teachers and the staff, uh, and all the student coordinators for making this possible.
Thank you, sir. Well, that was one interesting session. So as we are coming to the end of the session, we hope you guys got a lot to learn from this. We would firstly like to thank Mr. Jason for investing his precious time in enlightening us in this topic. So, last but not the least, we would like to thank all of you for patiently listening to the session and for a great response. Thank you. Thanks, everyone, and have a nice day.
Thank you.